What is epoching and why do we need it? As you remember, we have two conditions: stronger and weaker bright square on the screen. We want to understand if in general pupil responds to such a stimulus independently on the condition, and whether there is a difference between the two conditions. We expect a strong hypothesis that during a brighter stimulus, the response will be stronger. The constriction of the pupil will be greater. How to do it when we have a continuous recording of the pupil with some presentations of the stimuli with a random variation of the interval between them. We need to sample a part of data around each presentation, the baseline before the presentation and the response after the presentation. Let's say 10 seconds before and 10 seconds after on the onset of each stimulus. And then we will have a data matrix of, let's say, 20 rows corresponding to the onsets, corresponding to the stimuli, and a large number of columns. If we take 10 seconds before and 10 after, it will be 20,000 samples. And then this kind of data structure is very easy and convenient to plot and to analyze, because each time point corresponds, each sample corresponds to a certain time point before or after the onset of the stimulus. And this is the for loop where we create this kind of matrix, which will be called epoch. We already have a variable onsets, which has 20 elements. We have time, and we have the indices corresponding to the samples where the time becomes greater than the given onset. We create a window of indices which takes into account the onset index, which is the first element of this array, post-onset, and we add a number of negative and positive indices so that we get a window of all the indices corresponding to the first epoch. And then from the time series of pupil size variation, we take just those. We take from minus 5,000 samples to plus 5,000 samples. So in total, it will be 10,000 samples in a row. And we will have 20 rows of the data. Let's obtain this data matrix. It's here, the epoch. And now we can illustrate where exactly those epochs were extracted in the following subplot graph. Here you see the number of epoch, the center of the epoch, which is the onset of the stimulus, and the borders of the epoch, which are shown in red lines. This is the first epoch, the second, the third, and so forth till the last one. Can we reject few epochs? Obviously, yes. We extracted the epochs not only from time series of the pupil size, but also from the val out sequence, which is a sequence of ones and zeros, valid and invalid samples. So we have a data matrix for the epochs of the logical array, where you can see all the missing or the rejected samples for each epoch. Therefore, if you compute the mean, it will give you a proportion of the samples which are rejected. And we can decide that we replace with not a number each epoch which is created from the data containing less than 75% of valid samples. Let me plot the initial epoch. The image scaled is pretty good for such a purpose. So those are epochs, a variation of the data, something consistent at the time of the presentation of the stimulus or slightly after the presentation onset. And after the next step, you will see that few epochs will be entirely missing there. Let's redo this graph. Those 4 epochs are entirely removed from the following analysis. The next trick to do is baseline correction, which is a good thing. Let's see all the epochs on one plot. You transpose it so that it is plotted correctly. Those are our epochs. And you see that there is a large variation of the initial pupil size before the onset of the stimulus, so that we can minimize this initial variation. We do the baseline correction, which is basically a subtraction of the mean. Use non-mean function so that it doesn't give us an error when we deal with not a number samples. All the samples before the onset of the stimulus, from 1 to 5,000. Yeah, let's run this sequence. And let's create another figure and plot the epoch again. So this is the old plot and this is the new one. And here you can see that the variation of the pre-stimulus data is somewhat diminished. The spaghetti became closer to each other. Good. Another trick we can validly do to make the life easier for the computer we are using is a downsampling. We simply reject 90% of the data and we keep each tenth data point. So before this procedure it is 10,000 samples, and after it is already 1,000 samples. Now the time came for the first statistical test. We use t-test and we feed there the epoch. So what we basically do here is the comparison between the baseline, which should be in average 0 because it has been subtracted from our data matrix. And most likely after the onset, we will be able to see a beautiful and clear, very significant reduction of the pupil size. That's it. So the confidence interval which is estimated will be plotted in green and the zero line in black. So we have some spontaneous false positives, false negatives, and a huge significant cluster after the onset, which is good and entirely predictable. Next, we will try to get the effect of conditions. In order to do this, we will load ResOut file, which is stored here. The ResOut is created by the experimental paradigm script, and it contains this randomized sequence of the conditions. Let me remind you that those are the brighter and less bright stimuli. And we do another t-test to compare those two conditions, condition 2 and condition 1. This is an unpaired t-test because we can have a different number of independent epoch for each condition. And we will see the confidence interval in another figure. That's the figure. We have average time series for condition 1, for condition 2. It looks like stronger in the condition 2 in red. But our statistical results are not that strong. What we can do to improve our statistics, we can try to use another statistical approach, which is Bootstrap. And this is how it is computed. The principle of the Bootstrap is that you randomly shuffle the samples for first condition and the second condition, and you estimate the distribution of the outcome, which is the difference of the mean of the two conditions. after the distribution is formed with a large number of repetitions, you know what is the likelihood of getting a randomly generated from the same data with random distribution between two conditions. The effect size like this. And we take the threshold of 5% of the distribution. And we will plot those two borders as another confidence interval in magenta color. That's it. And as for me, it looks somewhat better than the t-test. In general, Bootstrap can be more sensitive than the t-test. And then there is another approach, also based on the Bootstrap, to estimate the statistics for the temporal cluster. We have this cluster, which is apparently significant, which is the upper limit of the confidence interval is is lower than the zero line. But how can we say if in general it is significant or not? We don't do any correction here, and we have a huge number of repeated measures. So it can be entirely spontaneous and not related to any real data. It can be false positive. In order to verify if this cluster is not false positive, we can run statistic on the cluster size or cluster volume, which is we try to shuffle many times our data and to estimate which size of the cluster, which extent, the length of the cluster, and which volume, which is the sum of all the points of the cluster, can be obtained if our data is not arranged according to the experimental conditions, but is arranged randomly shuffled each time. And this kind of approach is not very fast. It takes some time to be computed, because you do the Bootstrap 2 times. First you do the Bootstrap for each point, and then you repeat this Bootstrap 1,000 times for different randomizations of the condition assignments. And each time you estimate the confidence interval, and each time you do the cluster measures. But then you have the rows of maximal volume in each attempt and maximal size of the cluster in each iteration. I will not run this procedure at the moment. It has been done before. And this is the stored result. Volume max is this. So sometimes there is nothing, sometimes there is some outcome, and we have 1000 attempts. And if we estimate the percentile of the size of the volume, we will see the threshold for the 5% of likelihood to get such a large cluster. The threshold for the size is 106. So this is the size, the extent of the cluster, 100 point, which is unlikely to be produced spontaneously by randomly shuffled data. If we compare this to our results, we can say if our cluster is longer or shorter than this threshold value. Our cluster size, real cluster size, experimental one, is stored in the variable, let me see, all original. It is still not there. Let's go there. All original is here. This 77 is the size of the cluster. And this is the volume of the cluster. And this is the onset of the cluster. This is not relevant. It just tells us that the cluster happened after 500, which is after the onset of the stimulus. But those two are important for us. 77 is already smaller than the threshold size. Which tells us that it is not likely to be sufficiently significant. Let's compute the volume, threshold volume. The threshold volume is 1300. At the same time, our volume, our real volume, is just 423, which means that the effect we get is not significant yet. Maybe with more repetitions or at the group level, it will become significant, but not at this moment. Well, we have just less than 10 presentations per condition. Therefore, it looks like the experiment is somewhat underpowered to prove the expected effect at the individual level. I'm sorry that I didn't go into detail of the cluster statistics and the Bootstrap. I think to add a separate video on this point, because I believe that this simple and exciting tool have to be discussed better for the beginners as well as for some advanced neuropsychologists, neurophysiologists, because it is pretty simple, pretty straightforward, and useful in studies of such kind of time series, psychophysiological measures, event-related responses, and so on. Thank you very much for your interest in this tutorial.